Hello class, this is Professor Vlachos. Today we are going to cover the topic of association rules. It's a very important topic because this is how data mining started. The whole field of data mining started from the concept of association rules. Therefore, it is important not only for historical reasons, but it also gives you a glimpse of how data mining can solve real-world problems. So, let's get started. Let's go and see what we mean by market basket analysis. The topic of association rules has started from market basket data, which appears very frequently in retail data. In this case, we assume that the shopper purchases a basket of products. You visit the supermarket and you take the basket or the cart and you put inside the various items that you want. Therefore, we have the concept of the basket and we have the concept of items that you put inside the basket or the cart that you wheel into the supermarket. Now the goal is, if we have this database of what each shopper has purchased, this time, the previous time, etc., from the supermarket, can we try to find patterns in the buying habits of users? Are there products that are typically bought together? And if we manage to find these patterns, how can we exploit it in a business perspective for a business goal? What we assume is data such as this, which every supermarket has. Therefore, they have in their database data of this type. This is the transaction ID, number 1, number 2, number 3, and so forth. This may be from different or from the same person, it does not matter. So every time you check out and you pay, it keeps a record of what items you have purchased. In this case, transaction 1, some particular shopper has purchased 2 items, bread and milk. In another transaction, someone else, or maybe even the same person, he has purchased bread, milk, diaper, and Coke. Therefore, the basket are all the items that someone has purchased, and the item is each particular thing in the basket. There are 2 interesting questions that one might want to answer having this type of data. Imagine you are Coop, or you are Migros, or you are Lidl. The first question is, which are the products that are typically bought together? And the second question is, if I find these products that are typically bought together, so the 2 questions, they are highly related to each other, can I predict for a particular basket, if I know that it contains other object X, how likely it is to contain an object I? This is usually denoted as set of X, so here I have many items with an S. How likely it is, having observed that the shopper buys all of these items, how likely it is that he will purchase item I? This is very useful for the case of recommendations, such as in Amazon. In Amazon you go, you have purchased in the past some items, you have put it in your online basket, and we can see that at the bottom it recommends certain particular items that maybe go together with this purchase. So it tells you, okay, if you have bought this, maybe you would be interested in this, in that, or the other. Which is data that is extracted not only from your buying pattern, but from the buying pattern of other users. Therefore, the second part is useful for recommendations, and the first part, I want you to think a little bit how it would be useful to use this type of interactions. If we understand that certain sets of products, they are bought together, how can we use it in a business context? Therefore, the first problem that we examine is how to identify frequent item sets. Given a set of supermarket transactions, can we find the items that are frequently bought together? If we have this set of transactions, we can say that diaper and beer, they are frequently bought together. So we see diaper and beer, they are bought together in one transaction, in two transactions, in three transactions. This is it. In three transactions. And milk and bread, they are purchased together in how many? Change the color. They are purchased in milk and bread in one transaction, two transactions, three transactions as well. We said we want the frequent item sets. An item set is nothing more than a set of items. We have one item set, which contains only one item, two item sets, which contains two items, and so on. The question now is, what do we mean by frequent? And this is where the notion of support comes very handy. So support for an item set I, that is for a set of items, if we have several items, it's the fraction of transactions or of baskets that contain this item set. So this is exactly what we did before, but as a ratio. How many transactions contain this item set? So let's say beer and diapers over the total number of transactions. This is the notion of support. What is the percentage of transactions that contain this item set? And item set is a set of items. Remember, it's not only one item. Therefore, we say that the item set, one or two or three item set, is frequent if it appears in at least S% of the basket. And this is something that the user gives. This is typically given as percentage, but it may be given as the number of baskets, in which case we call it typically support count, and we represent with the Greek sigma. For example, we can say the support count for beer is 5 baskets, so it appears in 5 of the transactions. So if you see it as a ratio, you should know that is as a number less than 1, or as a number between 0 and 100, you should know that it is most likely the ratio. If you see it as an integer, 5 baskets, you should know that this is the support count. Let's see an example. We have this set of transactions which consists of 1, 2, 3, 4, 5 items. We have item beer, item Coca-Cola, juice, milk, and pears, which we represent with the initial letter. So this will be represented in the below transactions as B, this will be represented as C, this will be represented as J, as M, and as P. And we want to find all frequent item sets, the one item sets, the two item sets that are frequent, 3 item sets, and so forth. So the longest one that we can find. And we consider an item set as frequent if it has support more than 3/8. I put it as a ratio here because I simply have 8 transactions, which means that what I want is something that appears in at least 3 transactions, 3 or more. We can start with the one item sets. Which one item sets are frequent? It is these 4. 1, 2, 3, 4. The pair is not frequent. Why? Because how many times does it appear? It appears 1 time, 2 times only. Do we want something that appears 3 or more times? All the other items, one items, are frequent. What do we mean by that? So the milk, in how many transactions does it appear? It appears in 1 transaction, 2 transactions, 3, 4, 5 transactions. Therefore, it is frequent. You can count by yourself for the other items just to verify that they indeed appear in more than 3 or more transactions. Now let's examine the 2 item sets. Now going on the 2 item sets, what can we see? One is milk and beer. So when does milk and beer appear together? In 1 transaction. Milk and beer, no. In 2 transactions. Milk and beer, 3. So it is already frequent. We don't have to go any further. Right, it also appears in 4 transactions. So it appears in 4 transactions. What else is frequent? Beer and Coke is frequent. So beer and Coke, okay, beer and Coke, it appears 1 time. Beer and Coke, no. Beer and Coke, 2 times. Beer and Coke, 3 times. Beer and Coke, 4 times. It also appears 4 times. Alright, note that the order here makes no difference. Here we see that we have Coke and beer, and here we have beer and Coke, but it still accounts as an item set, right? So the order is irrelevant here. Order is not relevant. We just care about the presence of an object. And also Coke and juice is frequent. You can see that it appears in more than 3 transactions, at least 3 transactions. Now what have you noticed? Have you noticed something? What you may have noticed is that the frequent 2 items, so the items that are too frequent, they were also frequent as 1 items. And this is easy to comprehend. You cannot have something that is too frequent if it's not 1 frequent. So for a 2 item set to be frequent, it needs to be composed of frequent 1 item sets. Similarly, for a 3 item set to be frequent, each of the 2 item sets must be frequent, etc. This is something that we will use later to make an algorithm that is efficient, or in an efficient manner computes how many frequent item sets we have. Otherwise, it would be a very expensive, a very costly job. This is called the monotonicity property or anti-monotonicity property, depending on how you see it. So we build on it monotonically. This is what it means. For a 2 item set, it has to be composed of frequent 1 item sets. Now, what are the applications? Why we do this task? Why do we care if some item sets are frequent? Imagine that people buy beer and Coke together. What can we do if we have this knowledge? Someone could say, okay, I can place the beer and the Coke in close locations in the supermarket to make people's life easier. So if there is an aisle, I can put Coke here, and maybe close by I can put beer. This is one way of seeing it. Someone else may say, okay, I actually do the opposite. I don't place them close, I place them far. if I know that people will definitely buy Coke and beer together, why not place them far, or maybe not so very far, so that at least they have a chance to see all these items in between, and maybe they buy also some of those. Which is the reason why the milk in the supermarket that everyone buys almost every day or every other day, it's not in the entrance. So if this is the entrance to the supermarket, if you have noticed, the milk is always somewhere at the end. So it's somewhere very far away from the entrance, because they know that everyone is going to go and buy milk. But on the path of going there, you are also going to see and potentially be influenced by all the other sales or the items that they have in sale, and you may buy them as well. Another perspective would be to give coupons for beers to those that buy Coke, or vice versa. Maybe this would be to incentivize someone that does not buy beer to buy also a Coke. Someone that does not buy them together, because we have observed that people typically buy them together, so we think it's a good bundle. Think of it as a bundle. Now, what is even more interesting is the following. Since you know that people buy them together, you can do the following. You can do a sale, you can run a sale on beer. So the price of the beer, okay, this is a bottle of beer, is going to go down. So imagine it costed 3 francs before, and now you price it at 2.80 francs. So the supermarket is going to somehow lose this 20 cents. And it has to find it from somewhere. But if we know that the Coke, so this is a Coke, Coca-Cola, which maybe, let's say, costs 1 franc. If you raise it to 1.20, so the price here is going to go up, the sum of these two is going to still be the same. It's still going to be 4 francs. It was 1 before, 3 francs for the beer and 1 for the Coke, 4 francs, and now it's still 4 francs. What have we done here is we have given the incentive to people to come and buy cheaper the beer, but we know that people are not going to buy the Coke from somewhere else. Most likely they will buy it from the same place. So why not increase the price of the Coke? The buyer does not lose any money. It's the same amount of money that he pays for the bundle. And the supermarket also gains the additional influx of people that come because there is a sale on the beer. So they sell more beers, but probably they also sell the same amount of Coke. Therefore, the supermarket doesn't lose, and also the buyer does not lose any money. Maybe sometimes he or she can even gain if they just buy the beer. Right? This is interesting to know. If something is bought as a bundle, you can increase the price or decrease the price of one to run an advertisement, and increase the price of the other part, that is the other object that is part of the bundle. I will give you an example. Washers and tumblers are typically bought together, and I was trying to find a combo washer and tumbler from Samsung. This is a model for the washer from a reputable online store. It costs 2,000 francs. And the tumbler that goes together with this washer, at the same store it was priced at 1,800 francs. So I said, maybe I can find this tumbler for a cheaper price from another store. I thought it was too expensive. The total for these two was 4,800, and I said, okay, maybe I can buy the washer from this store, which is reputable, and buy the tumbler from another reputable store. How much would this cost? So I started looking at the different comparison sites and I found, okay, you could find the tumbler for 860 or 900, but I didn't want to buy it from separate places. So I said, okay, let me see if I buy the tumbler from this store, can I also buy the washer at the same store to save me the trouble of buying the washer from somewhere else. So it was, remember, 800 for the tumbler, 860, but whoa, the washer is 4700, so the total is 5600. It's actually worse than the 4800 that I had before from this store. Okay, I said maybe this was one thing, let me look in some other store. What happens? I look into this other store, again around 4700, so the total is again around 5600, it doesn't change so much. I search another store which costs 910. Here this is slightly cheaper, but again more or less it gives 4600. So what is happening here? Of course these shops, they know that these products they are bought as a bundle. They have run the association rules algorithm. They know that people buy this together. So usually they have one very cheap and they have the other one very expensive. If the people buy the bundle, they spend the same amount of money no matter where they buy it. A lesson learned: if you want to buy a washer or a tumbler as a combo, buying it from the same store won't save you any money. Of course, what we examined is for market basket, but this concept can be extended for other examples. So we saw cart and we saw products in a supermarket or in an online store. But you can use this concept of frequent item sets also in other settings. Now imagine that the basket is the transcript of the student. Now the items are the university courses. If we run association rules here, what would we get? We get the courses that are typically bundled together, they are attended together by the students. Similarly, the basket can be a person, the concept of the basket, and the items can be the movies. If we run association rules here, we can see which movies are watched together by the people, so we can find the habits of people. We're going to find that action movies, people that watch action movies, they typically watch action movies, many action movies. Typically, people that watch romantic movies, they watch romantic movies. People that watch horror movies, they bundle it together with other horror movies. Therefore, what you can do is, if you find that a particular set of items, set of movies, they are watched together, so we have movie 1, movie 2, movie 3, movie 4, which are typically watched together by running association rules. And we find that a person has watched movie 1, 3, and 4, but has not watched movie 2. Obviously, this is a good movie to recommend to watch. And this is how Netflix works. They find these patterns in the buying habits, and based on what you have watched, they recommend you the next movie to watch. The one that goes well, if you have watched movie 4, okay, and if you have watched movie 3 and movie 1, oh, you haven't watched movie 2, this is something that I can recommend to you. Similarly, you can see other cases. It could be the basket or the transaction could be the restaurant customer, and we have the menu items, or it can be the patient and the drug and the side effects, or it can be document and words. If we are examining the example of words and documents, here the basket is a document and we have all the words that have appeared. Of course, the text is ordered, but here we keep it as a bag of words. So we don't care about the order, we just care about which words appeared in this document. If we run this, we can see that we are going to find patterns, words that appear frequently in many documents, so student and school, or baseball and basketball, etc. Therefore, we are going to find words that are associated, that appear in the same context. You can say that they are semantically similar, even though they may have nothing in common with respect to the root of the word. So coach and game, they have nothing to do with each other lexicographically. So they have, maybe how many? They just have one letter in common. Okay, but the concept is very close to each other. Alright, so now we have seen up until now how to find frequent item sets, or not how to find, but how we define frequent item sets. So frequent item set is something that appears more than S times or than S% in the transactions, given by the notion of support. The second question that we want to answer is how to find these association rules. Association rules means that given a set of items that occur together, another item I frequently occurs together with those items. This can be represented as S leading to I, or you can have it as the set. This means a set S leading to I. The left part of this formula is called the antecedent, or the left-hand side, LHS, and the right part is the consequent, or the right-hand side of the association rule. So all of this is one association rule. Some examples: if I have this set of transactions, I can find that diaper is associated with beer, or milk and bread is associated with eggs, or beer and bread is associated with milk. How to read this is that if a basket contains milk and bread, it is very likely that it will also contain eggs. And we are going to see how to define this very likely. The ideal association rule, and this is an area where association rules are applied very, very frequently, is in the medical domain. Imagine that we have a large transaction of patient's symptoms and the interventions, that is, the drugs that they took. If we run an algorithm to find these association rules, we can learn something of the following. So if someone takes drug 1 and drug 2, this most likely leads to nosebleeds. This would be the example of a side effect if you take both of them. So even though a drug on its own may not cause nosebleed, if you take both of them, it may have some undesirable side effect. This is something that you can learn by running an algorithm to find association rules on a dataset with patient symptoms and drugs that the patient has taken. In order to find these association rules, we have to define some parameters. To find the rules of this type, what do we need to define? How large is this set? What we can do is we can specify some minimum set size for S or some maximum set size. We only care about item sets which contain up to 3 items or up to 5 items. Of course, the more items that you put, or the less items that you put, the more rules you are going to have. As the item set gets bigger, something is going to become more and more infrequent. So, occur together, what does it mean? Of course, this is the notion of support, right? So, when we say occur together, this is the notion of support for the S. And when we say another item frequently or very likely occurs with them, what does it mean? Here we have to define another notion, another concept, which is the confidence. Therefore, for association rules, so now we are past the item sets. If we have an association rule, how do we find support for an association rule, not for an item set? It's the number of transactions that contain both S and I over the total number of transactions. So it's similar to before. Before we had just frequent item set, just this maybe part, which was the S only over the total number of transactions. Now we have both of them since we care for both. And the confidence of a rule, so how likely a rule is to happen, is the number of transactions that contain both S and I over the number of transactions that contain S. Right? This is the confidence of a rule. Now we don't care, right? So you see that it's just the denominator that changes. An example, we have these transactions and we care about the association rule milk and diaper most likely lead to beer. Now, what is the support of this? It's the support count, how many transactions all of the items appear together. So they appear in two transactions, in this transaction and in this, over the total number of transactions, over 5. So the support is 0.4 of this one. And the confidence is, again, how many transactions they appeared. So they appeared in 2 over how many milk and diaper. So the left part appeared. The milk and diaper, they appeared in these 2 plus this transaction. So they appeared in 3 transactions. Therefore, the confidence is 0.67. Why do we need these 2 parameters, the support and the confidence? We need to measure the support because we don't care about rules that have very low support that may happen by chance. And why do we measure confidence? Because low confidence rules are not going to be reliable, right? So we need both of them. Therefore, in order to find association rules, we have to find or to specify these 2 thresholds, the minimum support and the minimum confidence that we care. So what we consider as important or as frequent. And I leave this to you as an exercise at home, given these transactions. If I care about minimum set size of 1, so I care for 2, 3, 4, etc., more than 1. And if I give support threshold of 0.5 and confidence threshold of 0.5, I leave it to you as an exercise to find which are the sets or the association rules that satisfy these requirements. And here there is also another concept which is important, which is the concept of lift. We have discussed about support, we have discussed about confidence. Now, what is lift? Some association rules may have high confidence because a particular item, so this item I, the right-hand side of the equation, appears very frequently. But not because it's associated with S, simply because it appears everywhere. We might find some rule that is spurious. What we can do in order to eliminate this is to divide by the number of transactions that contain I over the total number of transactions. Therefore, lift is going to measure interestingness of a rule. The greater value for lift, the more interesting the rule. Let's see this with an example. Again, this is the definition of the lift, so we do the same as before, right? Like for the support, but we divide this support number by this ratio. If lift is going to be 1, there is no association. If lift is more than 1, there is an association, so the rule is interesting because between the antecedent and the precedent. And if lift is less than 1, it means that something is not very interesting. Therefore, what we have here, we have this set of transactions. We have 5 transactions. milk, eggs, juice, milk, juice, cookies, eggs, chips, etc. And we want to estimate the lift of these two rules. So which of the two rules is more interesting? If we calculate the support for both of these rules is 2 over 3. So this is the confidence. So the confidence of both of the rules is 2 over 3. But if we divide by this number, we can see that cookies, it appears in much fewer transactions. Therefore, this rule is more important, more significant than this rule. Why? Because milk appears in almost every transaction. Milk appears here, 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 in 4 out of 5 transactions. This is what we say here. Therefore, even if it will appear most likely together with most of the other items that we have in the transactions. That's why you see here that the lift is lower. It's 0.83. Whereas here it's 167. This is a more interesting rule, even though both of them, they have the same confidence. A note here, finding that some items there is an association rule between them, this does not represent any sort of causality or correlation. So X leading to I does not mean that X causes I, and X leading to I can be different from I leading to X. Therefore, we shouldn't consider it as a type of correlation. Unlike correlation, whereas if two items they are correlated, X and Y, this is the same as Y and X. Therefore, you should not consider the association rule as a correlation. What we care for association rules is to be actionable rules, so it contains high quality and actionable information. Can we use it for something? It is not trivial, it is not something that we already know, and ideally it's not inexplicable, especially in the medical domain. If we find something that we cannot explain, most likely we need to do further experiments. We cannot simply use it if we cannot explain it. The problem is that trivial or inexplicable rules, especially if you have many items and many transactions, they are going to happen most often. You're going to have many of these spurious rules. Now let's try to figure out an algorithm to find these association rules. We said we have to provide these two parameters. And what we could do is simply generate all the possible item sets and find if they satisfy these two requirements, and then proclaim it as a frequent item set and as an association rule. So we could list all the possible association rules, we could compute the support and the confidence, and we can prune everything that fails these two thresholds. But generating all of those is going to be computationally prohibitive. You can imagine that this is a combinatorial problem. We don't want to go down this path. The question here is, can we devise an algorithm which is efficient for mining these association rules? For this, we have to look a little bit deeper into the problem in order to understand its characteristics. Let's see an example of these rules. All these rules, they consist of these frequent item sets: milk, diaper, and beer. If I find that these three item sets are frequent, they appear together very frequently, so it's a frequent 3 item set, I can try to generate all of these association rules, right, by splitting them differently. So once I take milk and diaper leading to beer, once I can take milk and beer leading to diaper, once I can take diaper and beer leading to milk. If I do all that and I compute the support and the confidence, I'll find out, of course, that the support does not change because it depends on all 3 items, not if they are antecedent or precedent. But what changes is the confidence. So all of these rules originate from the same item set. They have identical support, but different confidence. Therefore, we can decouple the support and the confidence requirements. We can start by finding item sets based on some particular threshold for the support, find the biggest one that we can find, or all of them, and then filter at the end based on the confidence. Therefore, we can generate all these item sets that are frequent, that we could compute the support and then filter the ones based on the confidence. Still, generating all of them is computationally expensive. Imagine that you have 1, 2, 3, 4, 5 items. With these 5 items, you can generate all of these item sets. Right? We have 1, 2, 3, 4, 5 as one item sets. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here, etc. 10 on the other level, and we have 1, 2, 3, 4, 5. So we have many items out of this, or item sets out of these 5 items. Many possible candidate item sets. In order to efficiently find the frequent items, we can use the property that we said in the beginning. If you remember the example with the beer, the Coke, the juice, and the pairs which were infrequent, if we find that an item set is frequent, this means that every subset is also frequent, or the inverse. If S is not frequent, then every superset of S can also not be frequent. How can we use this? Imagine that we find that the item set AB is infrequent. It does not satisfy this. It is lower than the support threshold that we have defined. This means immediately that all of the other supersets, they can never be frequent. If A and B is not frequent, then ABC, ABD, AB, so all of these item sets, they don't have to be generated anymore, they don't have to be counted, we don't have to count their support anymore. This is very important, and this is how this Apriori algorithm works. This is one of the probably the most influential paper in data mining. So how does it start? It starts in the beginning. Okay, you set a minimum support of 3. I want at least an item set to appear in at least 3 transactions. I start in the beginning with the 1 item sets. I do the count, I count how many times it appears, and then something that is infrequent, something that does not appear in 3 or more transactions, I delete it. And then I generate 2 item sets based only on the frequent 1 item sets. I don't have to consider anymore the infrequent. So here, if eggs can be notated with the letter E, if I find that E is infrequent, then everything that contains E, so all of these items that you see here could be eliminated. So if this was eggs and I find that eggs is infrequent, you can see that I have, sorry, not all of them, of course, everything that contains, it's not everything here, but everything that contains E could be eliminated. All right, this is from here, but this could be eliminated, this as well, these, etc. All right, so you see that you can eliminate many of those items that are infrequent, and you continue like that. You see from these two item sets which are frequent, you eliminate those that are not frequent, and you go on generating items. So if you consider every item for every stage, for stage 1, for stage 2, for stage 3, you should have counted the support of 6 items here, 15 items here, 21 items here, for a total of 41. Now, how many, if you do this pruning, how many do you calculate? You calculate 6 here, okay, you have to do it for all of them. But here you eliminate 2, therefore you calculate the support only of 6 items, and for the final stage you see that you only have 3 frequent item set that you have to count. Alright, so you generate 13 datasets or 13 item sets, or you calculate the count, the support for 13 item sets out of 41 that you would have if you didn't consider this more smart algorithm. This is the Apriori algorithm. This appeared 93, 94. Again, probably the most cited paper in the data mining literature. If you see 26,000 citations, this means that 26,000 other papers, they have referenced this work. They said, okay, I have used somehow this approach. 26,000. This is a very big number. Typically, if you have more than 100, this means that the paper is influential. Now, if you have 26,000, this is something that completely changed the field, or really started a new field. Therefore, this is the Apriori algorithm. You start in the beginning by generating the frequent one item sets, and you count how many these are. So this is the L1. So which items are frequent based on this support threshold that you give. You give all the transactions and the minimum support that you need. And then you repeat k equals 2. You try to find which items are frequent. You generate a candidate set, ck. So this is, you generate the C2. Which are the candidate things that I should examine their count using the L1. So you use this and you take the different combinations, you generate the candidate sets, then you count the support of this and maybe you trim some of those, and then you continue like that. Right? You continue like this iteratively for 3, 4, 5, etc. Let's see how this works with an example. Imagine that you are interested to find for this very small set of transactions the rules that have mean support of at least 50% and minimum confidence of 70%. This we'll use at the end. In the beginning, we'll just find the frequent item sets because the association rules is based on the frequent item sets. So in all the first steps, we'll use just this number. 50%, what does this mean? It means it appears something, an item, in at least 2 transactions. First step, find the candidate 1 item sets, C1. These are all the items that I have, and I count in how many transactions they appeared. A appears in 1, 2, 3. So I put the 3 here. B, it appears in 1, 2 transactions. I put the 2 here, etc. So which are frequent? I care something that appears in at least 2. Therefore this, the D, E, and F, I can eliminate them. And whatever remains are the frequent 1 item sets. And using this, I can generate the candidate item sets, the candidate 2 item sets. How can you do it? Remember that I need the combinations here. I need out of these n items, out of these 3 items, to choose 2. This is typically denoted as 3 choose 2. If you do the number, this leads to 2 item sets. And then I go into my database, I see how many times do I have A and B. I have it 1 time, and there is nothing more. I have it one time. For AC, I have it one time, two times, and that's it. So I put 2 here. For BC, I have it one time. This is it, so one time only. Therefore, this and this transaction is less than 2 that I need. I eliminate them. Therefore, this is the only item set that is frequent, the 2 item set that is frequent. Do I need to go any further? No, because I cannot augment it with anything. I cannot combine it with anything. So here I stop. There is no 3 item sets that are frequent. Now, from this AC, this is a frequent item set. How many rules can I generate? I can generate 2 rules, so A leading to C or C leading to A. The support, as we said, is going to be the same because it has both of the items. I care, now I use the confidence. For minimum confidence, 70%. What is the confidence of A leading to C? Let's think about it. The confidence is what? How many A and C appear together? A and C appear 2 times together. So it's 2 over 3. Okay, the 3 comes from how many transactions A appears. So A appears in 1, 2, 3 transactions. So this is 2/3. And the C leading to A, so this one, is again 2 over how many times, how many transactions C appears? It appears in 1, 2 transactions. So 2 over 2. Therefore, this is 1. Confidence of 1, it's greater than 0.7. This is the only rule that satisfies my criteria. Okay. And it's easy to see that A, okay, in this transaction, it holds here, it does not hold. So in 2 out of the 3 times, this is what the 2 out of the 3 means. Whenever I see A, I also see C. But here, if I see C, the confidence is 1, I always see A. So here I see C, oh, and it has an A. Here I see C, oh, and it has an A. And in nothing else I see C. So all of the times that I have seen C, I see A as well. This is what confidence means. Whenever I see C, oh, 100% of the times I expect to see A. This is a very, very important rule. Therefore, what we have examined today is market basket analysis. We saw the definition of a frequent item set. What is a frequent item set? And how we can use it to extract the association rules. We saw with an example the Apriori algorithm. We said this is one of the most influential algorithms in data mining. And we examined 3 concepts. The concept of support for both item set and association rule. So it's mildly different, the notion of support. We saw the notion of confidence. This is only useful for association rules. And we also saw the confidence of lift for association rules. And the lift tells you what? How significant, how important a rule is. Is it trivial or not? The goal is to eliminate or to lower the importance of something, of a rule that involves items that appear in every transaction. This is a rule that probably we don't care about because it is a spurious rule. This concludes our treaty on association rules. I hope that you got a glimpse of how important association rules are, not only for finding patterns, but also for extracting some useful insights about your business. This was it from me, so thank you for attending this online lecture. and I hope to see you also on the live session.